Okay, so in the previous lecture we had completed the discussion on the cyclic decomposition theorem, right? So in this lecture we are gonna move towards certain important results which require the cyclic decomposition theorem. But before that we need to quickly recall a few things which we had done previously. For example, the concept of we will briefly recall the facts. For example, we have studied the concept of an invariant direct sum, right? If you remember, so we had studied the concept of a invariant direct sum, and we had said that if V is a finite dimensional vector space, let's say V is a finite dimensional vector space and T is a linear operator defined on V. Suppose there is a direct sum decomposition of V of this form, okay, plus Vk, let's say, and this linear operator, if you restrict it to some one of these Vi's, we write it as Ti's, then this linear operator T can also be written as the sum of each of these linear operators, these restricted linear operator. Also, we say that this Ti is induced by T. This is one more term we use. Important fact which we want to discuss, that recall we had said that suppose beta I is an ordered basis of Vi. Okay, so if beta is an ordered basis of Vi, and let's say uh, the matrix of the linear transformation Ti with respect to the ordered basis Bi is given as some A1, AI, let's say. Okay. And what should be the dimension of this AI? The dimension of AI is, let's say, it's Di cross Di, where this Di is the dimension of the subspace Vi. One thing also I should have mentioned here, that each of these Vi's are T invariant. That's why the term invariant direct sum, right? So we had these to be T invariant. Clear? Okay. Now, if you uh, consider a sequence of these ordered bases, say B1, B2, we have K of those spaces, so Bk, and you consider this to be a basis of B, which will indeed be a basis of B, then the matrix of the linear operator T with respect to B is of this form, right? So it's of the block diagonal form A1, A2 till AK, where each of these A1s are these matrices, right? This is what we had studied previously. Okay, and yeah, so this will do. And one more important direct sum decomposition theorem we had studied, which we had called the primary decomposition theorem, right? So let me just quickly recall the primary decomposition theorem. You will find all these uh, topics in the lectures present in the playlist, important topics on linear algebra. I've covered in details each of these topics. So what does the primary decomposition theorem say? So we have T to be a linear operator on a finite dimensional vector space V. I'm writing it in brief. V is a finite dimensional vector space over some field, let's say F. Okay. Small p is the minimal polynomial for T. Okay. Small p is the minimal polynomial for T, and we have a certain form of this minimal polynomial, which is given as P1 to the power R1, P2 to the power R2, so on till we have, say, Pk to the power Rk. Okay, where each of these Pi's are distinct, irreducible, monic polynomials. Monic polynomials over F, right? And each of these Ri's are positive integers. Okay, we had this in our hand. Then we said that if Wi is the null space of PIT to the power Ri, okay, where I is equals to 1 to K for sure, then V is a direct sum decomposition of these null spaces. So it's W1 direct sum, W2, so on till Wk. So this is the first point. Number second is that each of these Wi's are T invariant. Each of these Wi's are T invariant. And number three, that if Ti is the restriction of T to Wi, then the minimal polynomial, for Ti is Pi to the power Ri. Okay. So this was our primary decomposition theorem. Yeah. And one more thing to recall is the concept of a nilpotent operator. The concept of a nilpotent operator. Yeah. So what was the nilpotent operator? So it is an operator n. Let's say over a finite dimensional vector space. V is a finite dimensional vector space over a field F. Okay. Then n is said to be nilpotent if and only if there exists a positive integer r such that n to the power r is a zero operator and this is not a zero operator. Okay. So this is the basic definition of a nilpotent operator. Okay. Obviously, we are not. This is not a mandatory situation that the vector space needs to be finite dimensional. But since for the past like 6 to 7 lectures, whatever we are discussing regarding finite dimensional vector space. So I've just included that in this definition. Okay, so in very simple ones, any random linear operator defined on a vector space is said to be nilpotent if you get a positive integer such that n to the power r is the zero operator and n to the power r minus 1 is not a zero operator. So in other words, r is the smallest possible positive integer such that this happens. Okay. So now let us come back to the discussions which were intended to do in this lecture. So obviously I will assume that the cyclic decomposition theorem is now done to the viewers of this lecture. So I won't be discussing about the proof of it or the statement of it anymore. Let us quickly come to a corollary of the cyclic decomposition theorem. The cyclic decomposition theorem have been proved in the previous lecture, or I should say previous two lectures. Okay. So the theorem corollary goes as follows. If T is a linear operator, on a finite dimensional vector space, V, then every T admissible subspace has a complementary subspace which is T invariant. And if you have done the cyclic decomposition theorem, then I guess it's very obvious from the cyclic decomposition theorem. Let me give the proof of it. Suppose W is a T admissible subspace, of V. Okay. If W is equal to V, right, then the complementary subspace W dash is simply the zero subspace, right? Okay. So let W be a proper T admissible subspace of V. A proper T admissible subspace of V. Okay. Now then we know what happens. Therefore, there exists non-zero vectors, alpha 1, alpha 2 till alpha r, such that V can be written as the direct sum decomposition of W direct sum, the T cyclic subspace generated by alpha 1 and so on till the T cyclic subspace generated by alpha r. Right? Now this part is by definition a T invariant subspace. Right? Is by definition a T invariant subspace. Because it's obvious, right? Each of these subspaces consists of vectors of this form, right? Right. So if you just multiply this, or I guess I should say compose this with the linear operator, or see the image of this vector over the linear operator T, then you will get another polynomial in T only, right? That should also be inside the T cyclic subspace of alpha 1, and that happens for each of these T cyclic subspaces. Therefore, it's obviously T invariant, and here we have a direct sum. So this forms the T invariant complement. This can be considered as the T invariant complement, right? Okay. Let us move on to the next important corollary. So what does this corollary say is that, again, suppose T is a linear operator defined on a finite dimensional vector space. So let T be a linear operator defined on a finite dimensional vector space V. Okay. Then what we say is that there exists a vector alpha in V such that the T annihilator of alpha is the minimal polynomial for T. The T annihilator for alpha is the minimal polynomial for T. Okay. And number 2 is that if T has a cyclic vector, or I should say T has a cyclic vector, if and only if the minimal polynomial for T, the minimal polynomial and characteristic polynomial for T are identical. Okay, so let's talk about the proof. Now the first proof, I guess it's quite a trivial case if you carefully observe. So consider the cyclic decomposition theorem. Consider the cyclic decomposition theorem with W naught being the zero subspace. Okay. Then obviously you have V as a direct sum of these T cyclic subspaces, right? Alpha R T. We had the T annihilator of alpha 1 to be P1, right? P1 was the T annihilator of alpha 1. But if you quickly recall what was another form of P1, so recall that we had defined Pk to be the T conductor of alpha k into Wk minus 1, right? This was the definition of Pk, the way we had defined Pk, right? So it was the T conductor of alpha k into Wk minus 1, right? So if I talk about P1, so that implies P1 is the T conductor of alpha 1 into W0. What is W0? It's the zero subspace. So it's the T conductor of alpha 1 into the zero subspace, right? Right? So what does this mean? Now P1 is the smallest, by definition is the T conductor, right? So it's the smallest least degree unique monic polynomial such that it sends alpha 1 to the zero subspace under under the linear operator T, right? So doesn't that immediately mean that P1 is the minimal polynomial for T? That means P1 is the minimal polynomial for T, right? What was the definition of the minimal polynomial? Okay, the definition of the minimal polynomial was precisely that P of T is identically 0. And this was the precise definition. And we have quite achieved that fact from here, right? Clear? Because one more definition we had of these PKs was that these PKs were the T conductor of the whole V into W naught. If you recall, if I do not use this definition, recall one more definition which we had used while we were trying to prove the uniqueness. Okay, in step 4, the proof of step 4, there we showed that P1 was actually the T conductor of V into W naught, right? If you recall, right? So if P1 is the T conductor of V into W naught, where W naught is 0, that means P1 sends every vector to 0 under the linear operator T, and that is quite the definition of the minimal polynomial, right? Right? This statement was from step 4. Okay, if you quickly recall what we had done in step 4, what we did is that we considered the T annihilators of the vectors alpha 1 and we had chosen another vector gamma 1. Then we had tried to show that each of the T annihilators actually are T conductors of the whole vector space V into the T admissible subspace W naught. Okay, here we have choose W naught to be 0. Right, I guess this part is completely clear. Okay, this part of the proof is completely clear. You can just write that step by step. I'm not going into details of the proof. Okay, and let's talk about the second part. Now, if I talk about the B part of the corollary we have. Now, obviously, we have already seen that if T has a cyclic vector in the I guess in the second lecture on cyclic subspaces, we had seen this, that if T has a cyclic vector, if a linear operator has a cyclic vector, then its minimal and characteristic polynomials are identical, right? Here we need to do the converse. How can we do the converse? Let me just write it like this, that if T has a cyclic vector, then its minimal polynomial and characteristic polynomials are identical, right? This we had done previously. Okay. Conversely, what we can say here? Conversely, choose the vector alpha from A. Okay. So we had chosen a vector alpha. Here what we did was that from the cyclic decomposition theorem, we chose this vector alpha 1. We showed that the T annihilator of alpha 1 is indeed the linear the minimal polynomial for T. So the vector we were concerned about was typically alpha 1. So choose such a vector. So if we go by the statement, so there exists a vector alpha such that the T annihilator for alpha is the minimal polynomial for T. So we choose such an alpha. Okay. Now obviously, if degree of the if degree of the minimal polynomial, if degree of the minimal polynomial for T corresponding to alpha is dimension V, then that would obviously imply that V is equals to Z alpha T. Okay, so that what so if degree of minimal polynomial is equal to the dimension of it, that exactly means that the minimal polynomial is identically equal to the characteristic polynomial, and if that happens, then v must be exactly equal to z alpha t. So by definition, alpha is the cyclic vector of for v, right? Cyclic vector for t. I guess it's clear. Okay. So now we have a very important theorem. Um, I will not give the proof of this theorem in this lecture. Um, I might try to give a hint of it, but I am not actually concerned about giving a proof to this. Or let's see. Let's see. First, let me write the statement of the theorem. Okay. So this theorem is called the generalized Cayley Hamilton's theorem. The generalized Cayley Hamilton's theorem. Okay. What does this theorem say? Now we know one concept of a Cayley Hamilton's theorem, that the characteristic polynomial annihilates the very specific matrix or the linear operator, whatever. Let's see what's given in the statement. Let T be a linear operator on a finite dimensional vector space V. Let P and F be the minimal and characteristic polynomial for T respectively. Okay. Okay. Then number one, we have that the minimal polynomial divides the characteristic polynomial. Number two, we have that P and F have the same prime factors. So P and F have the same prime factors. Okay. And number three, we have that if we have a certain prime factorization of f, so if I can write p as f1 to the power r1 and so on till fk to the power rk is the prime factorization for p, then we have the structure of f given as f1 to the power d1 and so on till fk to the power dk, where this di is given as the nullity of fit, I guess to the power ri, correct, yeah, divided by the degree of fi, yeah, divided by the degree of fi. Okay, so this is the generalized Cayley Hamilton's theorem. Okay. Okay, so first thing first is that we have the concept of a sort of a prime element in the polynomial algebra. So let me just quickly give a formal definition to the prime element. What we mean by a prime element in the polynomial algebra. Okay, so yeah, let's go on to the next page. Okay, can this color be seen here? No, I guess. One sec. Okay, let me use this color. Correct, yeah. Yeah, let me do this with this. Okay, so a non-scalar irreducible polynomial over f over a field f is called a prime polynomial over f. Okay, is called a prime polynomial over f. It's called a prime polynomial over f, and also called the prime in fx, and also called the prime in fx. Okay, So this is the prime element. So these are the prime elements which we are talking about in this theorem. Okay. So let's quickly give a proof of this theorem. Let's do it, because we have already given the proof of every required theorem. So why should we leave one of them? So proof. Okay. So let v be not equal to 0, because if v is equal to 0, then that's a trivial case. We have nothing to do. What we do is that we use the cyclic decomposition theorem first. Okay. So consider the cyclic decomposition theorem. The cyclic decomposition theorem on V, considering W naught to be the zero subspace. So that implies, so we are abiding by the terms we had used in cyclic decomposition theorem. So that implies P, which is given to be the minimal polynomial for T, is exactly equal to P1. P1 was the T annihilator of alpha 1, if you remember. So for the T annihilator of alpha 1. Okay, so it's the T annihilator of alpha 1. And so P1 is exactly equal to P. This we had done in the previous corollary as well. Okay. Let Ui be the restriction of T to the T cyclic subspace Z alpha T. Okay. Then these are statements from the first lecture on cyclic subspaces. Then that implies Ui has a cyclic vector. Ui has a cyclic vector, and recall we had also said that in this case, if Ui is the operator induced by T on Z alpha I T, then the T annihilator of alpha I is typically the minimal polynomial for Ui as well. So the minimal polynomial for Ui is both so Pi is both the minimal and the characteristic polynomial for Ui, right? So the minimal polynomial and characteristic polynomial for Ui are both Pi's, right? Okay. So therefore the characteristic polynomial is f is of the form P1 P2 till PR. Yeah, that's PR, and this comes exactly from the block diagonal form of the matrix, if you recall. Okay, because if you quickly go back to what we did here, yeah, here, right? So each of these V1, V2s are the cyclic subspaces we were talking about, right? So this Ti is what we symbolized as Ui. Ui will have a matrix representation of this form. So doing a similar case, we will get the block diagonal form of the linear operator T, which we are working with, of this form. Now obviously Pi is the minimal polynomial for Ui. Therefore that means P1 is the minimal polynomial for this, P2 is the minimal polynomial for this, so on. Pk is the minimal polynomial for this, right? So the minimal polynomial of f should be of the form P1 times P2 times Pk. Sorry, the characteristic polynomial for T must be of the form P1 P2 till Pk, right? And so that implies P obviously divides f as P is equal to P1, right? So P1 divides f, that means P divides f. Furthermore, if the minimal polynomial divides f, that means any prime divisor of P will divide is a prime divisor of f, right? There that implies so every prime divisor of P divides, or I should say the prime divisor of P is a prime divisor of f, is a prime divisor for f. Okay. Conversely, what we can say about these prime divisors? Consider a prime divisor of f, because we have said that the they are having the same prime factors except for multiplicity, right? That was the statement we had. So if you quickly go back to the theorem, so the same prime, okay, I have not written this, except for multiplicities, except for multiplicities. So if they are having the same prime factor, so we need to show that every prime factor of P is a prime factor of F and every prime factor of F is a prime factor of P. Okay. So every prime divisor is a prime. So conversely, what we can say is that, if let's say let P, I should use let G be a prime factor of F. Let G be a prime factor of F, then that implies G must divide Pi for some I, right? Because F is of the form P1, P2 till Pk, Pr, right? But if G divides any of the Pi's, then that means G divides P1, which is equals to P. Because recall the property of the ET inheritance we had, Pi plus 1 divides Pi. So if G divides any of the any of the polynomials Pi, it will divide P1, and P1 was exactly equal to the minimal polynomial, right? So G divides P, so G is a prime factor of P as well, right? Is it clear? Okay, so yeah. So the last part of the statement is coming from the primary decomposition theorem precisely. So let the prime factorization for P be as given. Okay. Yeah. So we use the primary decomposition theorem. We use the primary decomposition theorem. That is, we can have a direct sum decomposition of V in terms of the in terms of the null space of each of the prime factors, right? So we use the primary decomposition theorem for the given P, which says that if Vi is the null space of Fi t to the power Ri, okay, then V is a direct sum decomposition of each of these, yes. Right? Right? Okay. And these Fi to the power Ri is the minimal polynomial, for Ti, where Ti is T restricted to Vi. Right? This is exactly the statement of the primary decomposition theorem. Okay. Vi is obviously T invariant subspace. It's the null space of a linear operator. Okay. So now what we can say? Now what did we have in part 2? Part 2 said that the prime factors of P and F are same except for multiplicities of this theorem, obviously, except for multiplicities. So now we can continue in this way, that since the minimal polynomial is a power of the prime Fi, since the minimal polynomial is a power of the prime element Fi, then the characteristic polynomial for Ti, it surely has the form Fi to the power Di. Di is clearly greater than or equal to Ri, right? Now obviously Di is basically dimension of Vi divided by degree of Fi. This is very obvious from the definition of a characteristic polynomial, right? Clear? Okay. Okay. So if Di is given in this form and dimension of Vi is dimension of the null space of fit to the power ri. That is exactly nullity of fit to the power ri, right? So the value of di is clear from here, right? But again, since V is a direct sum decomposition of these operators, each of these operators are T invariant, but then T is obviously a direct sum of these individual induced operators. So it's T1 plus T2 and so on till Tk, and then from this decomposition, it's obvious that F should be of the form Fi to the power Ti, sorry, F1 divided by D1, F2 to the power D2, and so on till Fk to the power Tk. Okay, so this was the thing. Okay. Now this statement, let's talk a very important consequence of this generalized Cayley Hamilton theorem. State this as a corollary. The corollary is that if T is a nilpotent linear operator on a vector space V of dimension n, then the characteristic polynomial for T is x to the power n. So what should be the proof of it? Firstly, quickly recall the definition of a linear operator. Since T is a definition of a nilpotent operator. So since T is nilpotent, okay, there exists some r in the set of positive integers such that T to the power r is equal to 0 and T to the power r minus 1 is not equal to 0, right? Let fx be equal to x to the power r, then f is the least degree polynomial such that f of t is 0, right? So by the definition of a minimal and a characteristic polynomial, it's obvious that r must be less than equals to n. The characteristic polynomial can be at most n degree. Equal to n degree. Okay, and the minimal polynomial, degree of the minimal polynomial must be less than equal to n. Okay. Now, if r is equal to n, we have nothing to show, right? Because the so this is indeed the minimal polynomial, right? By definition. Also, by definition, f is the minimal polynomial. Whereas the least degree monic polynomial is the minimal polynomial for t. Right? Clear? Okay. Therefore, if r is equal to n, we have nothing to show. It's trivial. Okay. So let r be less than n. Okay. Let r be less than n, and consider p is of the form. Consider p to be the minimal polynomial. We are actually relating it to the previous theorem. In order to relate this with the previous theorem. So how we are trying to relate this? By taking f1 to be x and r1 to be r, right? Therefore, p has this prime factorization of f1 to the power r1, which is exactly equal to x to the power r, and it's obvious, right? And this is clearly a prime element. It's an irreducible polynomial, okay, abiding by the definition of a prime element in fx. Okay. Now, if this happens, so what can we say about the? So therefore, the characteristic polynomial f should be of the form f1 to the power d1 where D1 is the given by the null space of F1t to the power R1 divided by the degree of F1. Okay. Now F1 t to the power R1 is exactly equal to t to the power R1. And this is the zero operator. Therefore, the range of this is the zero subspace, or in other words, the rank of this is 0, right? We are working inside a finite dimensional subspace, sorry, the finite dimensional vector space of dimension n. Then for the rank nullity dimension theorem, it's clear that the nullity of this should be n, right? So that means the nullity of this f1t to the power r1 must be n. So that implies d1 must be n upon degree of f1. Degree of f1 is 1. So d1 must be n, right? Therefore, f takes the form x to the power n. Clear? Now it's very easy to verify as well, because if you have a linear operator t such that t to the power r is equals to 0, then it typically corresponds to a matrix A as well, such that a to the power r is equal to 0. You can manipulate this matrix a bit to have this. Okay. A quick hint is that every eigenvalue, if it is possible to achieve every eigenvalue of this matrix, let's say the field is algebraically closed. So every eigenvalue can be achieved of this linear nilpotent matrix. These matrices are called the nilpotent matrix, right? So the every eigenvalue is 0 for a nilpotent matrix. Yeah, whatever. So I guess this part is clear, right? Now let us come to a very important definition. Let me just not write definition quickly. Let me just explain a bit. We are intended to see the matrix analog of the cyclic decomposition theorem. So we have an operator T defined on a finite dimensional vector space V. Okay. V abides by the cyclic decomposition theorem. You can think of W naught to be 0 subspace, right? Let Bi be the cyclic ordered basis alpha I, T alpha I, and so on till T to the power Ki minus 1 alpha I be the cyclic ordered basis for Z alpha IT, where we choose dimension of Z alpha IT. It's clear from the cyclic ordered basis to be Ki, right? Okay. Now we know in the case of a cyclic subspace, if I restrict T to this, let Ti be the restriction of T to Z alpha IT, then so Ti has a cyclic vector, then T can be represented as the companion matrix for the minimal polynomial for Ti, which is Pi precisely. So therefore Ti can be represented as the companion matrix for Pi, right? Therefore, if B is so each of these subspaces are also T invariant, so we can use the concept of an invariant direct sum. So if B is considered to be the sequence of the basis elements, basis B1 till BR, let's say, then I don't have space here, right? Yeah. Then what should be the matrix of T with respect to V? The matrix of T with respect to V considers a block diagonal form A1, A2 till AR. All these elements are 0, where AI is the Ki cross Ki companion matrix for Pi, right? Clear? Now let me give the definition. Now this sort of a representation is called direct sum of matrices. Okay. When you have a matrix which is given in a block diagonal form of this form, it is called a direct sum of these individual blocks. Okay. The definition is that an n cross n matrix, which is the direct sum, of companion matrices of non-scalar monic polynomials p1 p2 till pr, such that pi plus 1 divides pi, I ranging from 1 to r minus 1, then the matrix is said to be in rational form. Clear? In such a case, each of these p1 p2 till pr, these are called the invariant factors. Or let us first give a theorem, then we will be precisely understand the concept of why we use the term invariant. Okay, there is a theorem. I won't prove this because this is very easy to prove from the uniqueness of the cyclic decomposition theorem. The theorem is that let F be a field, and let B be a n cross n matrix over F. Okay. Then B is similar over F to one and only one matrix, which is in rational form. Okay. Use the above observation, which says that if you consider the linear operator over Fn, let's say B is an n cross n matrix given, right? So if you choose a linear operator over Fn, which is represented by B under certain ordered basis, then obviously B can be considered to have a representation in a rational form with the above observation we did, right, before defining the rational form. And then you can choose another representation of B in rational form, but that would imply existence of another set of vectors and another set of T annihilators for the cyclic decomposition theorem, but by the uniqueness they should be same, and hence the two rational forms are indeed should be same. Clear? Okay. Use this exercise. Okay. So since this every matrix is has a unique rational form, or is similar to a unique matrix in rational form, and these linear operators are what gives which give the rational form. That's why each of these polynomials are called the invariant factors. Okay. The polynomials for this matrix B. Okay. The polynomials p1, p2 till pr, which give the rational form, are called invariant factors. For B. Okay. And we will be later giving an algorithm to find the concept of invariant factors. Okay. Clear? Yeah. Okay, so let this lecture be up to this much. In the next lecture, we will give a brief example on rational form, and then we will be moving on towards our main concern, which is the concept of a Jordan form. And after we give an algorithm to calculate the invariant factors, then we will also be carefully we will be having enough tools to construct the the rational form of a matrix. Okay, yeah. So meet you guys in the next lecture.